we'll be talking about Big Bang nucleosynthesis. As we said, temperature in the early universe was at some point sufficiently high so that processes which otherwise, for example, would only happen inside the sun, that is fusion processes, would happen in the universe. And so there's, when you talk about these effects, there's however a big difference between what's happening inside this like a stellar fusion source. That is, whereas a stellar fusion source does not evolve rapidly, it basically just keeps on producing fusion reactions all along. The universe as such was always expanding at the same time. So there's always two competing processes. The one process is the actual rate with which the, for example, nuclei can collide to start fusion processes. And the competing expansion basically tends to dilute the nuclei, which makes the rate with which the interaction takes place go down. So there's essentially two time scales that we're talking about. So the one time scale is the collision time scale, or the interaction time scale, and the other one is the expansion time scale. So the expansion time scale is very simple. That's essentially just 1 over h. And since that is going to be then, that's just a over a dot. And since we know that any processes which would be sufficiently energetic, like these ones, would only be happening in the time when the universe was in the radiation-dominated phase, we know that this a over a dot goes with the radiation density, 1 over the square root of the radiation density. This is essentially just coming out of the Friedmann-Lemaitre equation, which says that if you're in the radiation-dominated universe, h squared goes with rho radiation. And so that h then is essentially rho radiation square root of. So this is 1 over the h, then this basically goes with 1 over the square root of radiation. So this goes like rho r to the minus 1/2. And since the energy density of radiation goes with 1 over a to the 4th, this goes with a squared. So the other rate that we're dealing with is the collision timescale, and that relates to some interaction rate. Let's call it capital gamma. And so the interaction rate will go with the density of the constituents times the cross section of this process that we're dealing with. And if we assume the cross section does not depend upon the temperature, basically, which is not the case, because when we talk about thermal processes, they go with sigma v, so there's always a dependence upon the temperature. But let's just, for the sake of simplicity, assume that we only deal with this dilution of n. Then basically this would go with 1 over sigma, and n goes, that's the number density, goes with 1 over a cubed, so that goes with 1 over sigma a to the 3rd power. So you see that no matter what you start out with, eventually the collision time scale will always grow quicker than the Hubble time scale. And so the universe basically expands in such a way that we do not have much collisions happening anymore. And so this is actually something which is very common in many cases when you deal with these kind of dynamic processes taking place. That is, the expansion is always competing with the rates of whatever reaction you're dealing with, and eventually there will be no, one of the interactions will not work anymore because the universe is expanding so quickly. So we can look at nucleosynthesis basically at a process which will take place at the time when the energy was sufficient, that basically we can deal with nuclear fusion reactions. And that would be basically at a temperature or an energy which relates to the temperature kBT of the order of MeV, because we know that's the temperature that we need to drive fusion reactions. Of course, it depends in the end also on the density of the nuclei, but let's assume this is sort of happening at MeV energies. Then let's talk for a moment about any kind of process that's ongoing in the universe which creates new elements. And there's not only the primordial nucleosynthesis, but there's other ways that we can produce elements in the universe. And so one of them is the well-known stellar nucleosynthesis process. That is ongoing in our stars and driving the stellar heat production. And these are usually fusion processes. And we have also, at the end point of a stellar evolution, we have explosive nucleosynthesis. So these are actually very important to produce heavy elements beyond, for example, iron. And so this is something which happens mainly in supernovae. And well, then we have the spallation. This is something we learned already in the cosmic ray part. So that basically produces, for example, some of the lighter elements, and this is related to cosmic rays. And then finally, we have the Big Bang nucleosynthesis. And all of these processes are relevant for the elements synthesis in our universe. However, they differ in their importance according to which elements we're looking at. So let me just pull this plot in for you, where we can see some of the elements and their places in which they're synthesized, or the epochs where they're synthesized. So you find, for example, in this plot now, this is starting with the hydrogen here, it goes up to oxygen and then fluor. And so hydrogen basically is assumed to be completely primordial. So that's not synthesized, that's just protons recombined with an electron. Then deuterium and 3 helium, 4 helium are mainly produced in Big Bang nucleosynthesis. And that also explains specifically for the 4 helium why that is a universal abundance. Because it doesn't really depend upon stellar synthesis, because stellar synthesis adds additionally some helium to it, but you see the fraction, this is indicated by the fraction of the blue part of the box, is small with respect to the part which is produced in primordial, or let's say Big Bang nucleosynthesis processes. Helium-3, for example, you see basically half of it is produced in stellar synthesis and the other half comes from the primordial processes. Now if you look at lithium-6 and 7, lithium-6 and 7 are both mainly produced in not in stellar processes, but mainly in spallation processes from heavier cosmic rays. So lithium-6, for example, is almost entirely produced in spallation processes, and the little bit that is still around, that's coming from Big Bang nucleosynthesis. And now this depends upon where you look. If you look, for example, at the cosmic ray abundance itself, you will find almost all of the lithium be produced in spallation. But on the other hand, all the lithium that you find, for example, in stellar systems is basically also produced by cosmic ray spallation that has been captured and reproduced in the material. Now, for beryllium-9 and beryllium-10, you again find this mainly spallation, and then you go on in the sequence, and essentially everything which is heavier than boron comes all from stellar nucleosynthesis, and there's then, of course, some additional points which relate to so explosive nucleosynthesis, which happens for the more massive and also for the more strong neutron-dominated nuclei to be dominating. Now, let's look at how actually Big Bang nucleosynthesis has been proceeding. And so this is a very complex dance, I want to call it, because there's many things happening in a very particular sequence, competing with the expansion rate, which is completely independent of the reaction rates, because the energy content is in radiation mostly, but the complex dance means there's lots of things happening at the right time, at the right rate, in order to produce exactly the abundance that we see today. And it's quite critical how much of this nucleosynthesis is taking place, because in principle, if you basically had everything, all the hydrogen bound into helium, for example, you would have no hydrogen left to form stars. So that's kind of an interesting story. But let's just go through the sequence. So let's start out at a much higher temperature. Let's say we start out with kBT to be of the order of GeV. So at GeV energies, we have still a thermal equilibrium. That is the processes which change protons into neutrons, like for example the capture of an electron going into a neutron plus an electron neutrino, basically works in both direction and equal rates, so that you basically have the same amount of protons and neutrons around. And also the same for the process that is a positron capture. You go into proton plus electron antineutrino. And these processes again work in both ways. And then you have also the decay working in the only way that it can decay is the neutron can decay into proton, electron plus an anti-electron neutrino. Now, in this kind of thermal equilibrium, it means that the fraction of protons to, sorry, I would write the other way around. I write neutron number density over proton number density. They are about unity, right? So because they are working in the same way, so there's no difference. Now this process here, where basically a neutron decays, we know that there's the binding energy gone. That's about 1.293 MeV. That's an important number. Because at some point you will have essentially once the temperature drops below that 1.293 mega electron volts, essentially it will always go only in, you will only have the way that a neutron can decay into a proton, but you cannot have the back reaction anymore of a proton going into a neutron. So that will be this arrow going from left to right will disappear, and that arrow from right to left will disappear. And essentially neutrons will then start decaying. And this happens at a temperature of about 10 seconds. Time of 10 seconds. So then basically the temperature will drop to a value of about the binding energy of the neutron decay. And then at that time you will have the fraction of neutrons fixed to protons. So this would be then Nn over Np will be given roughly to a Boltzmann suppression. So this will go with minus EQ over QBT. So that's about round about then it's going to be about e to the minus 1. So you fix that fraction roughly, and then the neutron will just freely decay to proton with a beta minus decay. And the thing which is to notice is that the next step, that is the moment that you can basically start having neutrons and protons going into deuterium, because that's the first heavier nucleus that's going to be forming at that time, depends very crucially on how much additional photons you have around. And let's have a look at why is that. Let's first look at the reaction process here. I'll just make a new page here as well. So the next step would be formation of deuterium nuclei. So that will be a neutron plus proton going into deuteron plus photon. And this process basically, of course, goes also the other way around. So a photon could photodissociate a deuterium to then have a neutron and a proton. And the binding energy is very, very small. So the binding energy is of the order of 2.225 MeV. So in principle, the moment that the photon energy drops below that binding energy on average, you would basically say, okay, then this process can start. However, the photon number density is so much larger than the baryon number density, that is the number density of protons and neutrons summed up, because these are the only baryons present at the time. And this fraction we call eta, that's defined as the number density of baryons over the number density of photons. And that value, as it turns out, is of the order of 5 times 10 to the minus 10. So there's 200 billion times, 2 billion times more photons around than there's baryons around. So for each baryon you have several billion of photons. And the reason why that is something which is hidden a little bit early in the universe. We're not being covering that, but it has to do with effects where you have to have baryogenesis happening in such a way that essentially in the end all baryons and antibaryons are annihilating, and there's only a very little number of baryons left. So that means that this deuterium can only form once the temperature is well below the energy of which is the binding energy of the deuterium. And as it turns out, we have to go about 26 times smaller. So once kBt is about the binding energy divided by 26, and this number comes from this eta. This depends upon the eta value in the end. And that's about, 100 keV. We would basically, slightly below 100, so 90 keV or so, we would start having then a deuterium form at an energy which is much, or temperature which is much lower. That means this process is delayed to about 180 seconds or 100 seconds roundabout. So between here and here, some of the neutrons will already decay freely because the mean lifetime of neutrons of the order of 10 minutes or so. So some neutrons will decay. And the number of neutrons which are left at the time is then simply given by this at the time of about 10 seconds when neutrons start decaying freely. And then you have to factor in the decay time of the neutron, and then you end up with a value which is about 1/7. Go from like this value is about 1 over E, then you go to 1 over 7th roundabout. Now, once you have then this delay taken into account, you get this number here, which is essential. Point onwards, the proceeding is essentially going through the various steps to create heavier nuclei, but the first bottleneck of the whole procedure is the deuterium. Without deuterium, you cannot form any heavy elements. And then basically everything is competing against the rapid expansion of the universe. And so to make this story short, you need the right tuning of the expansion rate and also the delay because of the ratio of the baryons to photons to have the right value to delay it such that basically you have the right ratio of neutrons to protons. Otherwise, you may have the trouble that you will not have the right amount of helium left. So what could happen is that if you produce too much deuterium, you lock up all the neutrons, and then basically you cannot go to heavier, and then you don't have any helium anymore, for example, you can form easily. Or you could have too little deuterium, and then you will not have enough deuterium to form heavier stuff. So it's really requiring the right tuning. And so what will happen then after some time is that you will lock up all the neutrons will be absorbed, and they will be forming then helium in the end. And you will basically have 4 helium formed. And if you take that number, how much helium can you form? And so what we want to look at is the so-called mass abundance, called YP, and that's the density of helium over the mass density of helium over the mass density of everything, of the total baryons. And so in our case, we can simply say, if we assume that all the neutrons go into the helium, that means that 2 times the number density of neutrons corresponds over the total number density of the neutrons plus the protons, because you have 2 neutrons per helium. Then you can basically say it's like this. And then you basically plug in, so this is 2 times, and then we use this ratio of 1/7. So that will be 2 times 1/7 times NP divided by, and N is 1/7 times NP plus NP. And then basically what you get is this is exactly 1/4. So this is 0.25. And that's the magical number because that's what we basically find today. So the values are slightly higher because there's also stellar production of nucleosynthesis happening. And this ratio of 1/7 really depends upon the actual value of eta, and therefore this basically is a measure. How much helium we measure today tells us what is the amount of baryons per photons. And also this fixes then all the other heavy elements. So for example, the deuterium for hydrogen ratio, or the lithium per hydrogen ratio, and so we can use that to basically infer the actual values. Let me just show you for a moment what's going on. So I got this nice plot from a classical paper from Wagoner, Fowler, and Hoyle to show you the actual network, what's happening, because I'm not going to go through the details, just brush through it here a little bit. And so basically, if you look at this, you start out with the elements which you form down here, and the primordial processes actually just stop here at the helium. They do not proceed much further because that's the one where you basically have all kinds of arrows pointing towards. So the arrows indicate whenever you have energy gain by or exoenergetic direction. So essentially, you can go from helium-3 going to helium-4. You have tritium going to helium-4. You have deuterium going to helium-4. And you also have processes, that is, beryllium-7 can become helium-4, and lithium-7 can become helium-4, and beryllium-8 can go back to helium-4. So essentially, you have one bottleneck, that is, you have to go through deuterium, and then basically with helium-4 you can start forming heavy elements, but there's not much that can happen there. For example, you have only one direction, so you can form beryllium-7 in this process here, where you have helium-3, or you have tritium going into lithium-7, okay? So that means that you basically absorb most of the stuff in helium, and there's only little ways out to produce beryllium and silicium, and these are the only heavy elements which are formed. So let me just show you some examples of measurements of these kind of things, so how that actually looks like in practice. And here's a measurement which I just grabbed for you, which shows the measurement of absorption lines in intergalactic space. So what you do here is you basically observe a bright source which is highly redshifted, but the light coming from that source passes through the intervening medium, and there happens to be clouds of gas in this medium, which is rather pristine in the sense that it hasn't been processed by stars. These clouds are not massive enough to form stars in them. So essentially the idea is that these clouds would be really clouds which are which have the abundance which is primordial. And then you basically can identify absorption features in these clouds. And here's just such a cloud system along a line of sight. So you see everything is shifted to the same velocity. That is the velocity of the clouds with respect to us. And you see various so-called Lyman absorption features. And in this case, you basically can identify that there's deuterium absorption features which you can pick out in the system. And the strength of this absorption feature can be used to infer, for example, the deuterium to hydrogen ratio. And so here it turns out to be of the order of 2.8 times 10 to the minus 5, 2.8 plus minus 0.4 times 10 to the minus 5. You see that the hydrogen absorption feature, which this one is much, much stronger, and the ratio can be determined just with one individual object to be at the level of about, with an uncertainty of maybe 25% or so. So the current best value is much, much more precise. So currently, if you look into, for example, a article in the particle data book, which summarizes current measurements, so in 2020, summarizing this basically gives you that the deuterium to hydrogen ratio is 25.47. I just want to keep the numbers here because this is how accurate this measurement is done. Plus minus 0.25 times 10 to the minus 6. So the nominal value is the same as in the system. So this is within errors consistent. So this is 2.5 times 10 to the minus 5, and this is 2.8 times 10 to the minus 5. But here the uncertainty is only 0.25 times 10 to the minus 6. So this is like one more digit which we can take into account as within the accuracy. Now, let me just show you then how this whole nucleosynthesis process evolves over time for a given value of the sorry, that's the wrong one. For a given value of the of eta. Just pull that in. Sorry, that took a little longer. There we go. So what you see here now is on the x-axis the time in seconds. And here's the mass fraction of these individual elements. So let's pay attention to the gray line. So that's proton, and the red is the neutrons. So the protons, basically, you can see here, they basically go down a little bit because at this point here you see some of the protons being used up for the processes happening towards heavy elements. So the neutrons, they decay slowly, so they basically have a very, very gradual slope, which is hard to pick out in this plot because over that time scale there's not much happening. But overall, at the beginning of nucleosynthesis, round about here, you start forming deuterium, and that's at about 180 seconds or 200 seconds after the Big Bang. And this is for eta value of 4 times 10 to the minus 10. And also there's another value which I didn't pay too much attention to. That's the number of neutrino flavors that are present. So that basically fixes then all the things which are happening here. So you basically start producing deuterium. This is 2 hydrogen here, so that's the green line. So that starts rapidly producing the maximum here. And then also you produce hydrogen to tritium almost following the same rate. And then basically the moment you start having the heavy elements, you basically start producing also the helium-3 and also the helium-4. And so you see that helium-4 production basically is finished pretty much after about 200 or something seconds. And then basically all the neutrons are absorbed. There's just, this drops by several orders of magnitude. And then you still have some neutron decaying after some time. and there's some processing still happening on the lithium level. But essentially, you see the dynamics are basically done, and all the neutrons are absorbed after about 300 seconds in this way, and you just have helium-4 produced. And then you have constant values of lithium-7, lithium-6, which is the more abundant one, and also some homeopathic doses of beryllium-7 happening here. Sorry, this is lithium-7. This is lithium-6. It's hidden down here. So lithium-7 is the one which is produced mainly, and also some of the 7 beryllium. And this final value that you get depends upon the choice of the eta that you put. And here I just want to show you some plot which summarizes that as well. So here you see now in this figure on the top, you see the 4 helium mass fraction. So this is a linear display as a function of the value of eta. And it is now scaled in such a way on the top of this graph to the baryon density. So this is omega B in terms of critical density. And you see this is 1% of critical density and with H as the same way as I had introduced it in the previous lecture. So H is used to scale the small h to scale the Hubble constant. So this is H times 100 kilometers per second per megaparsecs. And you see that the value actually is changing. The value of helium depends on the density parameter in the way that this basically is scaled with eta. And you see that the yellow part is basically the measurement, and you basically can conclude from this that the actual value, so that's the value, that's the uncertainty here on the value for helium, because this depends upon the way you measure it, to be sure that you are not biased by stellar nucleosynthesis. And then you would constrain from this the value of omega B to be between slightly above 1% and going maybe up to 2, 3 and slightly above 3%. Okay. Now, if you do the same game with the other species, so for example here, this is the blue line is deuterium abundance over hydrogen. So this is not mass abundance, but this is just deuterium over hydrogen ratio. And there you see this is the measurement which I quoted before. This was the 2 point something times 10 to the minus 5. And these are the uncertainty, which are tiny. Then you would basically draw here the uncertainty on the value of the baryon density, and you would end up with a value which is between 2 point something and 2 point something. So it's like a little bit more than 2% in terms of critical density. And for the 3 helium, the measurement is much more complicated because 3 helium is mainly produced in stellar systems. Then you've got 7 lithium. There the measurements are a little bit different. Again, it's also having the trouble that 7 lithium is measured in the context or in competition with stellar fusion processes. And you see that the measurement is also having some uncertainties here. But now the curve for the lithium dependence on the baryon to photon ratio has a more complicated shape because lithium is first destroyed by is destroyed by increasing number of baryons, whereas at some point the production process overturns and then you produce more lithium. So that makes it a little bit more complicated. So that's why there's a minimum. However, the value that you would infer in terms of the baryon density would be somewhere between this value and this value. And that's a little bit below what we would determine from the deuterium. So that's something which is a little bit of a tension with each other. Nevertheless, keep in mind there's some uncertainty in the way that you determine the primordial lithium density in the observations of stellar systems, where you always have to assume some processing of stellar material. So to summarize, let me just write this down here. At the end, we have from the measurements of the mass fraction of helium and deuterium over hydrogen, we determine this eta baryon, and from that we can determine also what that is in terms of the the energy density in baryons in units of critical density, and this turns out to be of the order of 2%. And that's a tiny number. keep in mind I already presented to you that the matter density is of the order of 30%. So that means that most of the material is not informed from baryons. And that's fixed by the nucleosynthesis, which tells us that whatever matter there is, it's not baryons, right? And that means that it's got to be something else. And what it is, we don't know, but we will talk about that in the following lectures.